Welcome to our webinar and thank you for joining us. We're excited to share with you some ideas about dynamic modeling of inverter-based resources, which represents one of the most important factors for bulk electric power system security. My name is Gabriela Andrade, and I am a marketing specialist here at GERS. I will be giving a brief introduction, followed by the more technical side of the presentation presented by Mr. Diego Rodriguez. Please submit any questions you have for the duration of the presentation, and we will read them at the end of the presentation. First, I'll give a brief introduction of our company, GERS. GERS is an electrical engineering consultant group that was established in 1981. To date, we have completed over 6,500 engineering projects and over 3,700 electrical studies in over 45 countries. On this slide, you can see the countries where we have carried out projects from our offices. Additionally, we have attached a handout of our brochure for you to learn more about our company. For this presentation, we will be accompanied by our GERS Power Systems Manager, Diego Rodriguez. Mr. Rodriguez is an electrical engineer with strong experience in power grid planning. He had developed tools for the T&D grids in North, Central, and South America, has a strong experience in dynamic EMT and security constraint optimization studies for large and complex power grids. Now, before we get started, we have two quick polls for you to answer. So if you can please respond to these, and we will get started in just a moment or two. So here goes the first one. Okay, we're going to go on to the next quick one, and just a few seconds on this one. Okay, great. Thank you for your votes there. And all right, welcome, Diego, and you may now begin the presentation.
Okay, thank you, Gabriela. Thank you very much. Well, as Gabriela mentioned, during this presentation, we will see one of the three series presentation that we would like to make related with inverter-based resources. The presentation is divided on three principal parts. We'll make an introduction about renewable integration. We'll talk a little bit about equivalent model using WEC models. Finally, we'll make a brief introduction about PPC controllers, electrical controllers, and some other generator interface that are required when you are studying inverter based resources. As an introduction, I'll just say that the Energy Information Administration, that is the principal agency of US federal statistical system, shows that the net generation for 2019 was around 4 million gigawatts hours. Yes, what is interesting here is that still the system relies on conventional units. Oh, relies on conventional units as coal and natural gas. We also have a good portion of nuclear energy and just a small amount of hydroelectric, and some other renewables are solar and wind. Yes, we see on the picture here, we can at least sum up near 60% of the generation from natural gas and coal, and near 18% of the generation from hydropower and some renewable uh, generation. So what is relevant here is that there are good opportunities for the new kind of power plants that are based on inverters mainly. I'm talking about wind, solar, and battery energy storage system to back down those coal and natural gas. Yes, just not only for the environmental benefits that they have, but also by the energy cost. Yes, the sun is it doesn't have any cost right now. As you can see here on this picture, there are other statistics that support what we just mentioned before, yes, and shows that there is a considerable decrease coal, in the coal energy sources, and there is another considerable increase in the natural gas as well as in the renewables. So still, there are big opportunities for renewable integration for the next couple of years. Yes, and those are just statistics from 2010 to 2010, 20. The same picture, at least, is showing out here for three different kind of resources. I'm talking about PV, onshore wind, and natural gas from 2020 to 2050. Yes, these three technologies collectively account for near 63% during that time frame. Yeah. As a result of that amount of integration, at least here at GERS, we have performed different studies with different kind of inverters from several manufacturers. Yeah, we have SMA, Power Electronics, T-Make, Huawei, Sangro, and ABB. Yes, our experience just shows more than 136 studies during the last 2 years, at least in Florida. It doesn't mean that Florida hadn't received more generator interconnection services. It's just a picture that the integration of renewables is is huge in at least in the Sunshine State. Yeah, most of the studies have been performed with power plant of sizes that goes from 40 MVAs to 75 MVAs, and they use several different models here. Yeah. What is interesting from this table is that you can see no different versions of the model, different revisions. Some of them have been created in 2015 and up to now have changed. What results from a technology change? Yes, actually, you know that grid codes have been evolving during the last decade. At the same time, parameter and controls actions have evolved as well. So that is an important part, and that is why we received several comments and actually requests from transmission planners in order to make these three sections related with inverter-based resources. There are several studies performed during the planning stage that offer some security for the transmission planner and actually for in future for the operator. Some of them are listed here. Yes, it's just a power flow, a steady state, a short circuit analysis, a transient state that involves not only electromechanic but also electromagnetics. You know that these inverters are based on different converters that switch too fast in scales of nanoseconds or milliseconds or microseconds. So it is important to at least consider two different transient states during the study of these units. Actually, there is another one that is the PV analysis that shows how the reactive resources will be changed when you have huge integration of these power plants. There are the different time frames in which you can perform the studies. Just steady state, as I just mentioned before, or there are others are transient states, yes, electromechanical and electromagnetic. For this session, we will just talk about the electromechanic time frame. Yes, transient that occur in milliseconds to seconds. Yes, maybe 10 to 20 seconds. Okay, so it is very important to talk about equivalent models. Yes, you know that the common configuration or a typical layout for wind turbines and actually photovoltaic plants is shown in the picture here. Yes, where you can see different individual units that are tied to a medium voltage collector system. Yes, that collector is at the same time connected to a collector collector system station where you can find a transformer that just boosts up the voltage to levels of transmission level. Yeah, so we're talking about 115 to 30 kV, and depending on the size for offshores, it's not crazy to talk about 500 kV. Yeah, the low voltage side, the inverters is around 480 volts or 600 volts, and just elevates voltage at around 13.2 or 34.5 kV. The collector, as you see on the picture, can consist of one feeder or several feeders, and one medium voltage to high voltage transformer, or two medium voltage to high voltage transformer. Normally, at least customer or GOs only requires one. Yes, they don't believe on the plan will require a second unit as a result of reliability issue or something like that. Reactive compensation is also important. So some of the customers or some of the investors prefer to have a compensation at the collector system station. Yes, in order to provide reactive power and avoid the reactive power produced by the inverter. Yes. Some of them are fixed compensation, some others switchable units. And there are a few ones that we have seen with SBC or StatCom in order to have a dynamic compensation of the collector system station. You want to see a single line diagram? This is an example. Yes, you see several different units. If you have a solar plant, sizes are around 2 to 3 MVAs. If you are talking about wind powers, you can reach values of 2 to 4 MVAs. And if you have an offshore unit, you can reach values of 6 MVAs. So in each feeder, you have different configurations for the inverter, for the PV panels, that are interconnected through a transformer, yes, that elevates voltage from 600 volts to 13.2 kilovolts. As you can see here, there are different sections for the conductors, yes, depending of the amount of power that that flows through the conductor, you have different sizes. For example, here you have a 6 AWG for the first inverter, but at the end of that feeder you will have a 350 MCM. Yeah, so depending on the power that flows on each section, you'll have different conductor. But performing a study and actually implementing this kind of model in a software is a bit tedious. So WEC just make or propose a model in order to perform the studies with a reduced or a simplified version of this single line diagram. Yes, that model is shown here on the right. And at least try to represent all the units, all the generator or the generation from the panels through just one generator here, one transformer, The collector system, I mean all the lines that comes from the collector side, uh, are represented with just one line that is a collector system equivalent. The other, the station transformer, normally as I just say, you will have only one, and the other one is the transmission line. Yeah. Some of the common mistakes that we have at least perceived is that some models don't include the transmission line and irrelevant. I mean all the model by itself is very relevant, and actually it doesn't allow like generic values. Yes, the idea is to have the final configuration that will be implemented on the system. So the parameters that you will use here, even during the planning stage, are the real ones that will appear on the system. This will have a big impact during the transient stage, since the idea is to capture an accurate voltage value at the POI, at the point of interconnection. So as mentioned before, you have some methodologies to perform and create an equivalent transformer. But normally that transformer is similar in all units, and the values are around 6 to 8% based on the MVA of the transformer. You will also have a collector system, and the collector system follows some kind of recommendation from NREL. Yes, that actually is based on the equivalent electrical moment in order to calculate it. I will talk a lot about that in the next slide. And finally, you will have a transmission line that just represent the interconnection line between the station and the point that had been suggested by the transmission planner. Yes, and depending on the voltage size, uh, I'm talking about 69 kV to 30 kV or 500 kV, you will have different breaker configuration in that substation. For the collector, I would like to talk about this one because it's very relevant, and it's very important to the to the model. NREL just suggests a simple method to have an equivalent for the resistance and reactance, and depends on the amount of power that is sent through each of these sections, as here. So basically you create like a moment depending on the number of units connected and the impedance of the system divided by the total number of the units in the system. You can create a table or actually try to automate the methodology and use that methodology to create the equivalent. The equivalent depends on the number of inverters interconnected in a section and actually the impedance on that section as well. So we have here an example. Let me just zoom in. Yes, where you can see the different sections on each feeder, the length, the conductor size, the parameters for resistance and reactance, not only on positive sequence, but also on zero sequence or negative sequence. Well, in this case, you won't have because you won't require during the steady state and transient analysis. And finally, you just follow the recommendation and methodology from NREL and calculate what the values are. Yes, basically they respond to the square of the number of inverters and the resistance and reactance. And at the end, you sum up everything that is interconnected to the main feeder. So you can calculate the real value for that collector system. As you can see here, it is common to find different cable sizes, conductor sizes. The capacitance of the equivalent probably is not realistic in the terms that this is a mathematical model. Yes, it doesn't, it just represents the reality, but it doesn't mean that you have that kind of parameters on a cable. So the final values are values that are big, yes, considerable big in comparison with normal conductors, but in fact this is just a mathematical model. And the capacitance or the parameter related with the capacitance are relevant in the sense that they are connected with using underground cables, and you know that in underground system the capacitance reach high values. So let's just talk a bit about the generic models. One of the main technologies that play a key role in generation and had required the development of these technologies, uh, I mean, of this kind of models, had been the wind turbine generators. Wind turbine generators have evolved during the last 50 years. Initially, they were conventional units directly connected uh, to the system. Most of them, and I guess all of them, were induction generators. After a couple of years, uh, some Europeans developed other system uh, that use one rotor induction generator with variable rotor resistance. You won't see any kind of inverter on these first two models. But after some years of development and with the new technologies of power electronics, Type 3 and Type 4 wind turbines appear. Yes, the Type 3 was partially connected to the system. Basically, they provide some control on the rotor of the machine, and actually the starter was directly connected to the system. In that case, you have some kind of flexibility for controlling the speed between plus minus 30%, and you don't require like an external reactive compensation as it's seen for the Type 1 and Type 2 models. And the other one, that is the one that probably is more important for this presentation, is the Type 4, that is a full-size converter. Basically, divides the grid in an electromechanical part and the other that is just electrical part directly connected to the power system. Since the evolution of the controllers, depending on each of the manufacturers, each manufacturer uh, at the start they just provided user written model or encrypted model, but was difficult for the transmission operator and actually for different consultants to base their analysis on black boxes. So people just started to talk about generic models, models that at least are understandable in the terms that they represent all different blocks, control blocks, and the user have some knowledge or idea about the parameters inside these blocks. I will say that most of the user-written models follows the logics presented of those generic models, but in fact there are some changes uh, dep depending on the manufacturer and the technology that they are using on the conveyor. Just to mention again, this is a Type 4 full converted wind turbine generator. Since you have decoupled the electromechanical and the electrical part on the left and right side, the models that are used for wind turbines are also used for PV plants. As mentioned here, the model uses power electronics to make a variable speed wind turbine generator using full power conversion, and actually can be connected to different frequencies. As I just mentioned, that represents a wind turbine or a battery system or a panel that are interconnected with an inverter to the power grid. There are two types of technologies for the inverters nowadays, grid following and grid forming inverters. Most of the technologies for these huge PV plants or wind turbine plants are grid following. What it means is that they depend of the ball power system. They just follow the signals from voltages and frequency in order to interconnect to the system. And they mainly control the current in order to avoid overpass the maximum capacity in the inverter. On the other side, there are green forming. Green forming inverters can produce a specific voltage magnitude and control the frequency. They don't have control, or the control is a bit loose for the current. Those could be used for isolated power grids, but I just mentioned in PV plants, big sizes, you will use just grid forming. So in case that you get isolated, your plant will be disconnected from the system. You cannot guarantee that will be providing any power to an island system. Okay, this is the same single line diagram that we saw before. There are several PV panels. There are different inverters. I mean, the same inverter with on their different locations, and are connected to a low voltage to medium voltage transformer. Yeah, this is a medium voltage PV feeder, and that go to a substation transformer that just would have the voltage to levels of 115 to 230 kV at the POI. At the same time, you have a PV plant or PPC controllers that communicates with the utility system operations center, and at the same time send signals to the different inverters depending on the values of voltages, frequencies, and power flows at the POI. Yeah, so this is the normal configuration that you will see on all different kind of plants. Yes, and the same picture that we saw before is represented with the WEC model. Yes, remember that at least PV panels are considered not dispatchable, although Q in the inverters can be changed even when there is not sun. They have low short circuit contribution current, a lack of mechanical inertia, high bandwidth, and they have other kind of specific characteristics as solar irradiance that are assumed constants. Uh, However, you will see that there are some controllers that at least try to simulate a drop in active power. So what you expected is that under frequency changes, you will change the dispatch of generation. But that is a bit limited, since you can, in the case that frequency just decrease, you cannot make the sun shine brighter. This model, the one that we will show here, that are used for electromechanical analysis, make negligible the representation of the DC converter side. The model is initialized with the power flow solution. Yes, we start with a steady state solution. And normally, or at the start, the NERC suggestion was to use the model in ranges around 3 to 9 cycles, but actually it can be used for faults that takes more time. I mean, 120 cycle as a single point of failure fault, or a breaker fault. The model usually is considered for power plants bigger than than 20 MVAs and provides a good representation at the POI. The parameters depend on the plant configuration and the controllers and the kind of technology that you are using for the converters. Similarly, the control schemes considers remote control, electrical converter control, grid integration, frequency and voltage protection. But those are not uh, in the models that we will show here. They are independent, but you need to model them in order to capture the responses after an event. Yeah. Probably we will not talk about the different issues on a protection system from IBR in terms of positive sequence and actually EMT during this presentation, but could be a part of a second webinar as well. During the transient response, the model combines fast inverter response and slow plant control. Yes, we are using in the inverter converter power electronics that is very fast. And in the case of the power plant, we'll use the almost the same methodology that we use for other conventional units. The generic model shall generate voltage spikes at the start or clearance of the fault. And that is the result of the integration step and the current injection models. Yes. When you compare an user-written model with a generic model, you'll see that generic model usually have a voltage magnitude higher than user-written model, and that is the result of how the model was implemented. Well, we are now on the part of the IBR models that I just showed before. This is the box representing the power plant controller. The other one, the REECA and REECB, uh, represent the interaction between that plant controller and the injection that will be appear on the network. You see here, you receive signals from the network, yes, as voltage, reactive power, active power, and frequency, mostly at the POI or at the transmission line that is used for the interconnection of the plant. And you generate some external uh, references for reactive and active power. Those signals goes into the inverter, and the inverter or the logic inside the inverter just creates some uh, active and reactive current commands. Those are those goes to the generator model block and are injected into the power grid. So we will discuss each control during the rest of the presentation. I just try to summarize everything here, but probably an hour is not enough. But it seems that today is a happy Thursday, so we won't want to spend more than an hour. So this is the controls that appear on a PPC. The model in the figure represent a different portion of that PPC controller. Yes, the first one allows droop compensation. Yes, through the current that flows to the interconnection line and uses the voltage and current signals. Goes through a filter and after that through a deadband. Yes, and finally injects into the system. The other one allows BiController that actually generates reactive power references, and the other that is independent is the active power. As you see here, you have the capability of allows active power drop depending on the frequency, or just have a fixed response for the active power branch. That is interesting on the inverter models is that you decouple the signals between active and reactive power. So that is good in terms that you have like independent controls, but can be difficult uh, when you are trying to match another parameters. So you have to be careful about that. But in terms of control engineers, it's easier at least to adjust most of the parameters. The first one is the voltage compensation using a line drop. Yes. So you will receive some, as I mentioned before, some voltage and current signals and move through this branch. Yeah. It goes through a filter and actually pass through a deadband and finally injects reactive power. There are some parameters or common parameters. This deadband usually is set up between minus 0.02 and to 0.02, and the error usually goes from minus 0.1 to 0.1 positive. Or other schemes or other manufacturers just disable this saturation here for the error. Okay, the next strategy is the QB control. You have two options here. You can capture the signals from the reactive power branch, from the reactive power, and goes through some kind of droop control. Yes, so what you have here is a droop QB characteristics, and that flows and follows the same kind of strategy here. Uh, Most of the manufacturers include a droop branch, but there are others that they don't allow droop compensation. But actually, it's based on NERC recommendation that parameters should be enabled. And the reason why is because when you have multiple units interconnected to the same POI, if you won't have the droop parameter or the droop constant, you can have weird interaction between the controllers of different stations. The other strategy here is only have a reactive power control, so you just capture the reactive measurement on the transmission line and you move under this control loop, yes, and generate the reference for the reactive power. Finally, in the power plant control, you can enable the response of the active power. So you will have different responses for different frequencies. What is important here is to take into account the deadband for that frequency that depends on the transmission planner and actually the regulation, and the droop for high frequencies and droop for low frequencies. So here is relevant to have this. This droop usually have a value of 20 that represent 5%. Yes, the inverse of 20, so 5% regulation that is required in US. The Normally, as I mentioned at the start, the PV only respond to high frequencies, so making a reduction on the active power that is injected into the grid. But if you want to inject more power uh, as a result of a low frequency event, will be difficult unless you have some kind of reserve in other sense, you will have to work in a suboptimal in a state of suboptimal maximum power point. The next model that had called the attention of most of the developers is the one related with inverter. As you see here on the right, it represents what the inverter will see. They have several parts, low voltage and high voltage right through part. That is the one that is here at part one. The other is a constant power factor. And the number two is just the QB control strategy. And that allows control not only local, but also using signals from the power plant. The other is the active power control that actually is a simple control that measures active power and passes through a filter and uses the filter voltage signals as well to generate a active current command. Just move through this whole section of the models. The part 1A just shows that under condition of over voltage or under voltage, you will activate this control loop. The others outputs in terms of current commands are frozen during this condition. So basically, when you have a fall that exhibits under voltage, the response will mainly follows this branch. Yeah. Normally, the values for this TRB are 0.02. Those are just filters of the voltage. And what is important or relevant here is that these deadband values normally should agree with the other magnitude that you have for over voltage and under voltage. So be aware of make these two the same. If you want to disable this logic, well, you can change the maximum and minimal voltage, or you can just set your gain to 0. The value for this one are commonly -1 to 1. Yeah. If we want to see some responses produced during a fault, what we will perceive is that we initially are providing some active and reactive power. Yes, the blue line shows the active power, the black line shows the reactive power. So when the voltage go down, the inverters reduces the active power, but as you see here, the response from the reactive power just follows a proportional, yes, a proportional control. So you have like a dead band, and after that you will get a response of that branch. As soon as you recover or clear the fault, you will go back and follow the rest of the control. Part two is a constant power factor. Constant power factor only uses the magnitudes from real power from the power flow and generates an initial set point for the control. And after that, you will get this one that allows QB control. What the name is QB is because you can go through these two BiControllers. The first one just is related with the reactive power, and the other one is related with a voltage loop. Yeah, that will allow local control. Yes, see if we don't use a power plant, this signal here, the reactive power, is constant and mainly will depend of how the model is initialized and your strategy will be. Yeah. For example, this is a constant local power factors. So you use the power factor calculated from the power flow and actually just make a direct and simple loop to create or generate the EQ command. The other strategy just follows the local Q control. So the local voltage, local Q control, sorry, the local Q control. So you only follows the reactive power here. Yes, no. So the initial point from reactive power will be your set point, as is seen here. The other one is the voltage or local generator terminal voltage control. So the result of this is how the model initialized or what is the reference of the model. Yes. So here, example, the reference will be this voltage that is results of a filter voltage. So you go back and initialize the point, the control initial point for this value here. So depending on how you initialize your control and which loop you select, you will follow a voltage strategy, yes, if this is the case, or a reactive power strategy, that is shown here, yeah, that uses the reactive current command. The last one probably is the most common that we have seen for a couple of inverters, not all of them, is this one that uses BiControllers. Uh, I'll say that is the most robust since they use not only the reactive power signal but simultaneously the voltage signals. So controls using this loop are faster than the other ones. If we compare uh, two strategies using a plant level Q control and a plant level Q control plus a coordinated QB control, you'll see this kind of results here. Yes, the black line follows a QB control, while the blue line follows just a simplified Q control. In this case, in terms of reactive power, they are kind of similar, but in terms of reactive power, you'll see that PIs, I mean this one, the second one, is faster. Yes, the black one reach some specific points faster than the other one. I will say that one is better than the other, but it depends of transmission planning guidelines and actually the point in which the inverter will be connected. And the other one, the strategy that the manufacturer uses for his product. Result of different combination, you'll have something like this table that, at least depending on the flag, on what kind of strategy you want to follow, you you will get different uh, kind of functionalities and different a mix of control strategies. The last portion or the last loop is this one that is an active power control. But mainly is just a first order filter. Yes, you won't have any control here unless you have a battery energy storage system. The the last the portion is related with the limitation of the inverter, is the current limit logic, and depending on reactive power or active power, you will have one or other kind of a strategy. So normally for transmission planning, you will get a reactive power priority in order to provide reactive power during under voltage events. Since there have been since inverters have changed during the last 5 years, manufacturers at least see that they have a special condition that was not represented on the previous model. So they integrate different functionality to the REECA. Yeah. Then you see something like a compensation loop, as shown here, that depends of state machines. Yeah. So basically, how it works is that during a fault, you have a voltage dip flag. Yes, you have a one here. Basically, activate this loop and move from a state 0 to 1. So mainly everything on the rest of the controllers just stay frozen. You keep the injection of reactive power, and after a while that you have a voltage dip 0, I mean that the fault was clear and you have recovered the voltage, you don't immediately go to the state 0. What actually you do is that you after a time you go to a state 2, you keep the same current signal, and after that the time is completed, you move back to 0 again. Just to show this kind of a response, I just created this picture in which you can see under voltage here after a fall, and you have an active current response, for example, here. Yeah. So what the model shows is that you move from a state of 0 to the next one, and during that state, most of the injector power is reactive, so all the active power is just 0. And after a time, yeah, just you wait for a time while the reactive power moves to the other control, and after that you start recovering. That caused some issues in California, uh, since that created an additional time for the momentary cessation that will be described with the next characteristic. The momentary cessation is represented with this block here. Yeah, what is momentary cessation? Momentary cessation is an inverter operating state where the power electronic, I mean the firing commands, are blocked such that both the active current and reactive current goes to 0. Yes. Sometimes only the active current go to 0, some others both of them. Yeah. And that is an underside condition. I mean, they keep connected to the power grid, but they don't inject power, so they create sometimes active power imbalance. I show here some of the results of that block. So you go here and see a fault that appear on at the POI. So the voltage just decreases. If you set this value to 0.7, as soon as the magnitude of the voltage that is being measured goes down from 0.7, you just get an instantaneous block from the active power, as seen here. And after you go upper than 0.7, you start to recovery, but that is limited by a ramp that depends on the inverter characteristics. The condition appear, or at least the momentary cessation and desired condition appear in an event on 2017 and had appeared another on 2018, where some faults appear on the system, yes, cause for a fire, and the voltage just drops near to zero point 0.9 per unit, and all the solars or all the inverter in the area decrease the power instantaneously. So the system just lost around 1200 megawatts. That caused a large frequency imbalance. So it's very relevant to set correctly those momentary cessation condition. We'll talk probably more about this on the next webinar. And finally, if you are including battery energy storage, most of the latest projects include some kind of active power reserve. You will have an extra control loop that only tries to show that the battery is charged and can be discharged into the system, or opposite that the that the system is that the battery is discharged and needs to charge from the system. There are some simulation here that shows the battery charging, yes, and reaching a state of charge of 1, or just discharging, yes, so it starts at providing 80 megawatts, and after a while just goes to 0 since the state of charge move from 20% to 0. The last one is a logic that depends on the generator and interacts with the EQ command, the commands from reactive power and active power, and how they are injected into the network. You have two blocks here, one for over voltages and the other for low voltages. So what you receive here are EQ command and just passes through a filter. This time constant are around 0.02 seconds. They are fast enough to represent an inverter. And you have here two loops. Yes, one for high voltage reactive current management. So you receive the signals from reactive current, and in condition where you have over voltage, you create an error signal that decreases the current. Yes, but you will never overpass the IO limit. I mean the maximum capacity of the inverter to decrease the voltage there, or to decrease the current. VO limit is around 1.2. If the manufacturer wants to disable this limit, just uses values high near to 2. Yes, value that will never be reached by the control. This part only responds to high voltages. If you have a normal voltage, you will generate a value less than 0, so the injection will be 0 here. Just because you have a saturation condition here at 0, and you have another limit here that, as I just mentioned before, allows to avoid overpassing the maximum capacity of the inverter. And the other one is just related with the low voltage active current management, says that actually measure the active current, and depending on the voltage, generates a smaller or a higher value of active current. This one tries to represent the response of the PLL during voltage diffs. There is also important here the RAM rate power. So this is relevant when you are recovering the power after a fault. So that is related with how the inverter will inject power to the system faster or slower, depending on the capacity of the inverter, and at the same time depending on the grid code requirement. So those are conditions that cannot be tuned. They depends on the design of the inverter. And that's all. Yes, I have to run and probably skip a couple of slides and a couple of descriptions, but thank you. I'm not sure if you have any question. So
Yeah, thank you for the informative presentation, Diego. Now we will begin with the question and answer portion of the webinar. If anyone has any last-minute questions, please submit them now. All right, so we do have some questions here. Our first one says, In your experience, how different are the responses from user-written models and generic models in real life?
Well, thank you, Gabriela. Well, that depends on the technology. Yes. There are some inverters or the latest version of the inverters have new control loops, so they considerable change some interactions. Normally before the fall or just after the fall and after the fall clearance. So I'll say that they are enough for the transmission planning, but when you want to see exactly the same response is not possible. Yeah, to have something completely similar, 100% similar.
Okay, we have another question here. It says, can we apply the power plant generic controller to different inverter brands? And if so, what would be the procedure?
Uh, okay, the generic control for power plant was designed for only one type of inverter. There exists some models or recommendation from EPRI to change or allow multiples output and multiples input from different uh, types of inverters. Yes. So right now, just the one that is allowed by WEC and actually NERC only uses one type of inverter. Yes. It seems that in future probably we'll have a power plant that interacts with several inverters, but right now we only have one power plant that interacts with only one type of inverter. Yes, right now it's not possible.
Okay, so we have one last question here. What is the recommended simulation time step to perform this kind of transient stability analysis?
Well, normally you should have a time step lower than the smaller time constant in the controllers. So the smaller time constant is around 0.02 seconds. Yes. So making probably half of that time constant is enough to capture the different transient response in the model. Mhm. Okay.
Okay, yeah, that's all the questions we have today.
Okay, thank you very much. Thank you everyone for attending, and we will probably share with you the next couple of webinars, even based on our time and then based on the response that you send for future sessions. Thank you.
Yes, great. Thank you, Diego, very much. And also, we have some our upcoming webinars right here. In September 24th, we will have our Arc Flash risk assessment webinar by our engineer Ricardo Cardona. And then on October 29th, we will have our microgrids automation webinar by Leniker Palacios. The registrations will be sent out on our social media pages as well as by email, so be sure to look out for those registration links. And thank you. Thank you very much for the presentation and for joining us today. And we look forward to seeing you all in future webinars.
Thank you, Gabriela.